Now let's have a look at the LTE Technology Basics. This slide provides an overview of LTE key parameters. First of all, the frequency range for LTE. So LTE can be operated in the FDD and TDD bands of UMTS. So on the next page we will also see what these frequency bands are in detail. The channel bandwidths for LTE. So there is bandwidths defined 1.4 MHz, 3 MHz, 5 MHz, 10 MHz, 15 MHz and 20 MHz. And each bandwidth actually is composed of a certain number of resource blocks. As you can see in this table, a resource block is defined to be 180 kHz each, and the resource block represents the smallest entity for a resource assignment. So a terminal or subscriber can be assigned one resource block or multiples of it. And this is true for uplink and downlink. So 1.4 MHz actually is represented by 6 resource blocks, and so on up to the 20 MHz being represented by 100 resource blocks. Modulation schemes that are available for LTE are QPSK, 16 QAM and 64 QAM, where in the uplink the 64 QAM is optional for the handset to support. Multiple access schemes for LTE are the OFDMA in the downlink, orthogonal frequency division multiple access, and single carrier FDMA in the uplink. LTE supports the MIMO technology. Actually, MIMO, multiple input, multiple output antenna technology, is very essential for LTE in order to support the high data rate and throughput requirements. In downlink, a wide choice of MIMO configurations is possible for LTE, and there's different MIMO modes supported. For example, there's transmit diversity, spatial multiplexing, cyclic delay diversity, and we can have a maximum of 4 antennas as the base station, which is defined in the standards, and also maximum 4 receive antennas at the handset, which is of course quite challenging. In the uplink, a multi-user collaborative MIMO is supported, so several users can share the same resource block assignment. We will see a detailed introduction to the MIMO at a later part. LTE peak data rates. In downlink, we can achieve 150 megabit per second with a 2x2 MIMO configuration, which would actually be represented by UE category 4. And we can even achieve 300 megabit per second peak data rate in downlink with a UE category 5, which would stand for the 4x4 MIMO setup. Both values are true for 20 MHz operation. In uplink, 75 megabit per second peak data rate in 20 MHz operation are possible. So please note, the peak data rates are really more theoretical values. They are not likely to be achieved in real life scenarios, because in real life you have certain cell load, you have certain radio link situations, which will not allow these data rates for a particular user. So nevertheless, the peak data rates are always quite useful to see, because they give you kind of a reference of what's theoretically possible with the system. So this table shows the LTE frequency bands that are specified. The table is actually taken from 3GPP specifications as of March 2009, and they are showing the specified bands for LTE operation. So there will be more bands added in future. For example, there's the work on UMTS LTE 3.5 GHz operation ongoing. So as you can see in the table, the bands 1 up to 17 are defined for FDD operation, and the bands 33 up to 40 are defined for TDD operation. There's some prioritization already defined, so there's a certain prioritization for bands 1, which is the existing UMTS band, band 3, band 7, which is the 2.6 GHz band, and band 13 in the 700 MHz arena. For TDD, band 38 and band 40 have a certain prioritization for real network deployment and for the first commercial deployments. But in principle, LTE can be operated in all these frequency bands. So now let's have a closer look into the OFDMA multiple access scheme and the downlink frame structure for LTE. So what is OFDM? In an OFDM system, the available bandwidth is subdivided into multiple subcarriers. And each of these subcarriers can be independently modulated. So typically you have several hundred subcarriers in a certain bandwidth, and they have a constant spacing of some kilohertz. The figure shows an example for the 5 MHz bandwidth, and you see the subcarriers. But of course, you can easily scale the OFDM principle also to higher bandwidths. Like in LTE, you have up to 20 MHz bandwidth. So compare the OFDM transmission with a single carrier transmission, for example for wideband CDMA. Since the multiple subcarriers in OFDM are transmitting in parallel, each one can transmit with a lower symbol rate, thus improving robustness of the technology for mobile propagation conditions. This picture shows the OFDM signal generation chain. So the modulated data symbols, which are going to be transmitted, are first parallelized, and then they are used as input bins to an IFFT operation. IFFT stands for inverse fast Fourier transform operation, which is taking place on the transmitter side in an OFDM system. This operation produces OFDM symbols. So actually we have a conversion from the frequency to the time domain here, and the OFDM symbols are then transmitted in the time domain of an OFDM signal. To each OFDM symbol, a cyclic prefix is appended as a guard interval to protect from inter-symbol interference. So this also means that with a longer cyclic prefix, radio channels with a larger delay spread can be addressed. So for example, larger cell, you would expect a larger delay spread, and therefore a configuration with a longer cyclic prefix would be helpful. On the receiver side in OFDM, you would expect an FFT operation to receive the symbols again and to convert again in the frequency domain. Now, what is the difference between OFDM and OFDMA? We have seen both terms already. So in OFDM, the users are allocated in the time domain only. So in this picture, you see on the y-axis the frequency domain and on the x-axis the time domain. And you see that user 1 has been assigned the full bandwidth, user 2 as well, and user 3 as well, and they are only separated in the time. Compared to that, on the right hand side in OFDMA, the users are allocated in time and frequency domain. So you see that user 1 is only using part of the available bandwidth, as well as user 2 and user 1, they can share the available bandwidth to a certain extent. So this is actually a very flexible scheme, therefore it is also used in LTE, because you can also, for example, exploit gains of frequency dependent scheduling. So you could exploit the fact that user 1 has a more beneficial radio link quality in a certain bandwidth area of the available bandwidth. So LTE uses a conventional OFDMA scheme. The picture shows an example for 5 MHz bandwidth, but of course you could also extend it to the other bandwidth values and scale it accordingly. So you see here the representation of the signal in the time and in the frequency domain. In the frequency domain, you see here the subcarriers represented. In LTE they have a constant spacing of 15 kHz for the regular configuration of the signal. And as we have seen, so you can transmit now and independently modulate on each of the subcarriers. The orthogonality of the subcarriers is also illustrated here. So in terms of the function here of each of the subcarriers, the frequency function, you see that where one subcarrier has a maximum, all the others have a zero crossing, which means that this is representing the orthogonality of the OFDM signal. In the time domain, you see the OFDM symbols transmitted, separated by guard intervals. In LTE, also we have a cyclic prefix as guard interval. Different configurations are possible. We have a normal cyclic prefix with 5.2 microseconds for the first symbol and 4.7 microseconds for the other symbols of a slot. And we also have an extended cyclic prefix for larger cell corresponding to 16.7 microseconds. LTE provides QPSK, 16 QAM and 64 QAM as downlink modulation schemes, so these can be assigned to the UEs in the resource allocations. So this picture illustrates a bit more the OFDMA time frequency multiplexing of several users. Again, the available bandwidth is organized in resource blocks of each 180 kHz, which is 12 subcarriers. So one UE can be assigned either one resource block, an example for this would be UE2, or multiple resource blocks, like UE1 has been assigned 3 resource blocks to transmit on. The subcarrier spacing is 15 kHz, and we can now see that each 1 millisecond these assignments can change. So the time domain in LTE is organized in subframes of each 1 millisecond, and one subframe corresponds to a transmission time interval. So every 1 millisecond we can change the scheduling decision, the base station can change the scheduling decision, and the distribution of the resource blocks among the users can change. Or it can also be maintained for the example of UE2. Now there's also the notion of a slot, which is 0.5 millisecond, corresponding to 7 OFDM symbols. The slot was introduced, for example, because the downlink reference symbols, also called the pilot symbols, are repeated every slot. So that's why it's also useful to have this notion of a slot. But for the resource assignment, again, the transmission time interval of 1 millisecond or subframe is the important part, because this defines the scheduling interval. So note that each UE can transmit with another modulation scheme. So depending on the radio link quality for each UE, either a more robust scheme like QPSK or a more sensitive scheme like 64 QAM can be assigned. Now let's have a closer look at the spectrum flexibility in LTE. We have seen that the physical layer supports any bandwidths from 1.4 MHz to 20 MHz in steps of 180 kHz, which is the resource block definition. But we've also seen that the current LTE specifications support a subset of 6 different system bandwidths for FDD and TDD, as they are also shown in the table. So this is these values of 1.4 up to 20 MHz, each corresponding to a certain number of resource blocks. The figure illustrates a bit more that the transmission bandwidth, which is actually then used in the downlink, for example, by the base station, is formed by the assigned bandwidths in terms of active resource blocks. The available channel bandwidth is a bit larger than the actual transmission bandwidth configuration of the cell, to leave some guard on both sides of the spectrum. Also important to note that all UEs must support the maximum bandwidth of 20 MHz, even though there may be smaller cell configurations available, and not all networks may support the 20 MHz depending on the spectrum that the operator has available. This slide shows the LTE frame structure type 1, which is the one for FDD operation, frequency division duplex. We have here the radio frame, which is defined as 10 millisecond, and that is the same definition as in wideband CDMA. One radio frame contains 10 subframes, and one subframe contains 2 slots. Now let's have a closer look to the subframe contents. So a subframe of 1 millisecond is illustrated here in this screenshot of a signal generator from Rohde and Schwarz. And as you can see here, this is a real signal. The x-axis is showing the time domain. So we see here an extract of 1 millisecond or 14 OFDM symbols for the normal configuration. And on the y-axis you have the frequency domain with 50 resource blocks, which is a 10 MHz signal. Now what is the contents of each subframe? In the beginning of each subframe there are certain control channels located, layer 1, 2 downlink control channels. So they for example, carry information about the scheduling decisions for the different UEs in a cell. So the UE would first read on these downlink control channels in order to get information whether there's resource assignments with user data inside the subframe coming up. So the actual user data allocations are represented in green on this picture. And you can see in this example that actually 2 users would share the available 10 MHz bandwidth, which is really just an example. You can also see at certain allocations downlink reference signals. And you can also see in this special subframe, which is the first one in a radio frame, that there's also certain synchronization and broadcast channels. So we have here in the middle in blue the primary synchronization channel, the secondary synchronization channel, and the physical broadcast channel PBCH, which are carrying predefined information important during cell search, which will be explained by Andreas in more detail later.
Christina, one question to the time plane showed by the signal generator. So what does it mean with the hashed area over the entire bandwidth? Can you explain it a little bit more in detail?
Yeah, of course. So the downlink reference signals, which are indicated here by the hashed areas, they are actually not transmitted over the whole bandwidth, over the whole 10 MHz in this example, but it's just indicated here the symbols which are carrying the downlink reference signals at specific locations inside. So it's specific subcarriers inside the indicated symbols here. So it is just for simplifications that we have hashed here these areas. And accordingly, this picture shows the LTE frame structure type 2 for TDD, time division duplex. The radio frame structure is the same also for TDD, that's 10 millisecond, subdivided into 10 subframes of each 1 millisecond. And we have also the notion of a slot of 0.5 millisecond. But of course, since it's TDD, there's a significant difference here, because in TDD we have uplink and downlink separated in the time domain. So this needs to be somehow reflected in the subframe structure as well. So let's also have a closer look at the contents of a subframe. So the table shows the possible uplink downlink configuration. So we have actually 7 different uplink downlink configurations defined for TDD. And as you can see here, it's indicated for each of the subframes of a radio frame whether it's carrying a downlink, denoted by a D, an uplink, denoted by a U, or whether it's a special subframe, denoted by an S. And you can also see that there's configurations with a downlink to uplink switch point periodicity of 5 or 10 milliseconds to select from. So let's have a closer look at one example. Let's have a look at the uplink downlink configuration 0, which is also shown in the screenshot again. So we have represented in the screenshot the 10 subframes, and so the subframe 0 would be a downlink one according to the table. So this is a downlink signal, and the green part is actually showing that there's user data in downlink carried in there. And again, subframe 5 is carrying the downlink data again. Then we have special subframes in subframe 1 and 6. The special subframe is actually carrying a downlink pilot time slot, a DWPTS, an uplink pilot time slot, a UPPTS, and a guard period. Guard period for TDD operation to switch from downlink to uplink. So downlink and uplink pilot time slot are used for regular data transmission as well. But they are just shorter because this special subframe has a specific configuration. Now the gray subframes which are indicated here in the screenshot, they are representing the uplink transmission. They are available for uplink transmission in this specific uplink downlink configuration 0. Also for TDD you have certain layer 1 and 2 downlink control channels defined at the beginning of each subframe, and you have also certain primary, secondary synchronization signals and a physical broadcast channel defined.
So far the downlink and the downlink frame structure. Now what about the uplink? In the uplink, as already mentioned by Christina, another transmission scheme is used, known as single carrier frequency division multiple access. What does this mean? First of all, we have seen that OFDM got advantages but also disadvantages. The major disadvantage of OFDM is the high peak to power average ratio, also known as crest factor. This is the result as this transmitted signal is the sum of all modulated subcarriers, and as some of them are in phase, high amplitudes are not avoidable. The high peak to average power ratio requires high resolution digital analog and analog digital converters, as well as very linear transmitter circuitry, as any non-linearity will cause intermodulation distortion, raising phase noise, causing intercarrier interference, and out-of-band spurious radiation. This is already challenging in the downlink, where we do have no trouble in providing power or space for the design. On the terminal side, this is nearly an overkill. The goal for 3GPP was to select another transmission technique for the uplink that keeps the advantages of OFDM, which is multi-carrier transmission and therefore an efficient use of the available bandwidth, and combines this one with the advantage of a single carrier transmission, which is, compared to multi-carrier, the lower peak to average power ratio. As the name already emphasizes, this is achieved with single carrier FDMA. Now, how a single carrier FDMA signal is generated from a high-level perspective. First of all, there's another block in the signal processing chain. A discrete Fourier transform is performed on the data symbols after serial parallel conversion, which transfers them from the time into the frequency domain. Afterwards, there is subcarrier mapping as in OFDM and an IFFT to transfer the signal from the frequency domain into the time domain. After the parallel serial conversion, the cyclic prefix is inserted. The last two blocks are the same as for OFDM, so there's no difference to the downlink signal generation chain. The DFT precoding is the essential difference between downlink and uplink. So what does DFT do? Well, first of all, it is a mathematical operation, but compared to OFDM in a downlink, where each subcarrier carries just one specific modulation symbol, the DFT takes the symbol and spread this one over the available subcarrier. In that matter, each subcarrier carries a portion of superposed symbols, therefore single carrier FDMA is also referred to as DFT spread OFDM. So this picture visualizes the things we just learned very well. When we compare classical OFDM used in the downlink and single carrier FDMA or DFT spread OFDM used for the uplink, then we can say that in OFDM each subcarrier carries only information related to one specific symbol. This is indicated by the color used for the subcarriers, as you can see on the left-hand side of the graph. In single carrier FDMA, each subcarrier contains now information of all transmitted symbols. You can see on the right-hand side in the graph that each of the different subcarriers carries now a little bit red, green, blue, orange, and so on. With this means with performing a DFT precoding, we shift around the problem of high amplitudes due to subcarriers in phase. Now the question that comes up is how the subcarrier mapping is realized in the uplink. There are two possibilities, each coming with one advantage. First, we do have localized mapping. In localized mode, the modulation symbols are assigned to adjacent subcarriers as shown in the graph. As shown, this would give us the advantage of multi-user scheduling gain in the frequency domain. For localized subcarrier mapping, single carrier FDMA is named as localized FDMA. The other mode, user distributed subcarrier mapping. In that matter, single carrier FDMA is referred to as interleaved FDMA. In this mode, the modulation symbols are equally spaced over the entire bandwidth. The advantage of this mode based on the robust transmission of control channels and the support of high mobility of the terminal. Now the question is which of the two modes is realized within LTE, and the decision was that the localized modes fits better to the overall system requirements. Further, both modes are impacting the peak to average power ratio differently. Again, the goal of introducing single carrier FDMA in the uplink was to lower the peak to average power ratio, enabling an efficient power amplifier design for the device. This chart shows the complementary cumulative distribution function, which describes the probability distribution of the peak to average power ratio. The CCDF is displayed for OFDMA, so for the downlink, and for both modes of single carrier FDMA, localized and interleaf FDMA. This data is taken from an article published in IEEE magazine back in September 2006, so in the very early days of LTE definition. The simulation uses a system with 256 subcarriers in a 5 MHz channel, where 64 subcarriers have been assigned to the user, which are in case A, QPSK modulated, and in case B, 16-QAM modulated. Further, pulse shaping was applied to the signal or not. In difference to 2G and 3G, there's no filter definition in LTE, means this is open to the design engineers. Just the defined in-channel requirements, for example modulation quality measured with the EVM, and out-of-channel requirements, adjacent channel leakage power ratio or spectrum emission mass, need to be passed by the transmitter design. In this simulation, a root race cosine filter was used with a roll-off factor of 0.5. As we can see, the crest factor for OFDM is constant at around 12 dB, which is comparable to WiMAX, and it is independent from the modulation scheme and the used filter. This is different for single carrier FDMA, especially for interleaf FDMA. For localized FDMA, which is the blue line, which is the mode which is used in LTE, the peak to average power ratio is in case of QPSK modulation around 8 dB and therefore 3 dB lower than OFDMA. For 16-QAM the difference is just around 2 dB. As already emphasized by Christina, LTE uses two modes: frequency division multiplex (FDD) and time division multiplex (TDD). The parameterization in the uplink is for FDD the same as in the downlink. The two different cyclic prefixes are used, normal and extended, giving 6 respectively 7 single carrier FDMA symbols in the uplink. For TD-LTE, the usage of the uplink depends on the selected uplink-downlink configuration, where each configuration offers a different number of subframes assigned for uplink transmission. But the parameterization of those subframes is of course equal to FDD mode and depends on the selected cyclic prefix.
So now let's have a look at the network and protocol architecture for LTE. When it comes to the network architecture of LTE, you will often hear the abbreviation SAE, which stands for System Architecture Evolution, and which indicates that also the overall system architecture for LTE was evolved, including the core network functionalities. The left figure on this slide shows the new network entities. The base stations, the so-called E-node Bs or ENBs, are directly connected to the core via the S1 interface. There is no radio network controller anymore as in wideband CDMA, so we have a very lean network architecture in LTE or SAE. The base stations are also interconnected with each other via the X2 interface. This is, for example, used to prepare handover situation and forward packets during handover. The right figure shows in more detail the functional split between a base station, an E-node B, and the evolved packet core network. The EPC or evolved packet core consists of different entities: the MME, which is the mobility management entity, the serving gateway, and the packet data network gateway. The base station, the E-node B, constitutes the evolved UTRAN, so it constitutes the radio access network, which also means that a lot of functionality is concentrated inside the base station. So you see the complete protocol stack for the radio protocols, physical layer, medium access control layer, MAC, radio link control layer, RLC, packet data convergence protocol layer, PDCP, and radio resource control layer, RRC, are part of the base station or are terminating in the base station. In terms of functions, this means that the base station hosts functionality for scheduling, dynamic resource allocation, measurement configuration and provision, radio admission control, connection mobility control, radio BIRA control, and intercell radio resource management. So there's really a lot of functionality concentrated inside the base station, a lot of intelligence. The mobility management entity on the evolved packet core side hosts the non-access stratum security protocols, the idle state mobility handling, and the evolved packet system EPS BIRA control. The serving gateway hosts functions for mobility anchoring, and the packet data network gateway constitutes the connection to the internet, for example, and functions for packet filtering and IP address allocation. This picture shows the protocol stack of the user plane over the air interface between the UE and the base station side. Actually, the names of the protocols you may already know from wideband CDMA. So we have physical layer, medium access control, MAC, radio link control, RLC, and packet data conversions protocol, PDCP. But the functional split is slightly different compared to wideband CDMA. The MAC is responsible for mapping between the logical and the transport channels, where the logical channels are defined between MAC and RLC, and the transport channels are defined between MAC and physical layer. MAC is also responsible for multiplexing and demultiplexing of data streams, for reporting scheduling information, and very important for the hybrid ARQ, automatic repeat request retransmission protocol, so for processing acknowledgements and negative acknowledgements received on the physical layer, and for deciding about retransmissions, for example. MAC is also doing priority handling and transport format selection, so in the base station all the scheduling is concentrated in the MAC layer. The RLC can be operated in acknowledged mode, unacknowledged mode, or transparent mode, so there's also an ARQ, automatic repeat request retransmission protocol, defined in RLC, resegmentation, segmentation, and concatenation, in sequence delivery, and so on. These are functions hosted in the radio link control. PDCP is doing header compression for IP packets, robust header compression. The ROC protocol is used there. So this is used, for example, to compress large IP packet headers and to improve the efficiency of transmission. Very importantly, there's a different functional split here compared to wideband CDMA. The security functions, ciphering and integrity protection, ciphering for user and control plane, integrity protection for the control plane, are hosted in PDCP as well. On the control plane side, the protocol stack is listed here. So again, you see the protocols between UE and base station over the air interface, as well as between UE and mobility management entity, which are the non-access stratum protocols. So you also have for the control plane, physical layer, MAC, RLC, and PDCP. And on top, on the layer 3, you have the radio resource control for the control plane, which hosts significant functionality. For example, broadcast of system information, initiating paging over the air interface, setting up the connections on RRC level, radio BIRA control, so controlling all the radio BIRA functionality over the air interface, releasing and establishing bearers, mobility functions like handover decisions, and UE measurement control, configuring measurement tasks for the UE and evaluating reports coming from the UE. On the non-access stratum level, we find the bearer management for the evolved packet system, EPS bearers, authentication procedures, mobility handling on paging origination and idle state, which is called ECM idle here. ECM stands for EPS connection management, and also security functions on NAS level. Now this slide shows the mapping between the logical and the transport channels for the downlink and for the uplink, which is defined for LTE. The mapping actually takes place inside the MAC layer, medium access control. So you see here the logical channels listed. For the downlink, that's the paging control channel, which is mapped onto the transport channel, the PCH, the paging channel. We have a broadcast control channel that can be mapped on broadcast channel or downlink shared channel. We have a common control channel, dedicated control channel, and dedicated traffic channel as logical channels defined in the downlink, which are all mapped on downlink shared channel. So you see here the downlink shared channel as a transport channel in LTE has a very important function.
Christina, one question to that slide showing the downlink channel mapping. You just explained that the broadcast control channel can be either mapped to the broadcast channel or to the downlink shared channel. How that can be understood?
Yeah, sure. So the broadcast control channel actually can consist of different, or can carry different types of information. The master information block is actually mapped on the broadcast channel, which is then mapped onto the physical broadcast channel. And the other types of system information are actually mapped onto the downlink shared channel. On the uplink side, we also have the picture here. So that's showing that common control channel, dedicated control channel, and dedicated traffic channel as logical channels are mapped onto uplink shared channel. And there's also a random access channel defined as an uplink transport channel. Now, these pictures are also illustrating that the protocol architecture for LTE was significantly simplified. And this especially becomes very visible when you compare to wideband CDMA HSPA and the logical and transport channels that are defined there and the mapping in between. So you see in LTE there was a reduction in channels that were defined to simplify the handling and to simplify the structure of the protocol architecture. Now, these tables show the LTE UE categories, terminal categories for downlink and uplink that are specified for LTE. The upper table is for downlink. 5 UE categories are defined in downlink, and they, for example, differ in the maximum number of bits, downlink shared channel transport block bits, that can be received in a 1 millisecond transmission time interval. That's the leftmost column here. So this column and these values also determine the actual peak downlink data rates that can be supported by a certain UE category. For example, if a UE of category 4 is able to receive around 150,000 bits in 1 millisecond TTI, this translates into a 150 megabit per second peak data rate. Another interesting criteria of the UE categories is the MIMO capability, the multi-antenna capability. All terminals in LTE mandatorily have 2 receive antennas, at least. But the first category, the UE category 1, does not support transmission on multiple layers. So it does not support a real spatial multiplexing, a real dual stream transmission. This is only possible from UE category 2 onwards, so categories 2 to 4 support a 2x2 MIMO setup with dual stream transmission, enabling the higher data rates in LTE. Category 5 even supports a 4x4 MIMO setup, because these UEs of category 5 would have 4 receive antennas, and they can then of course also support corresponding data rates of up to 300 megabit per second. Again, these are theoretical values which you would not see in a real system, because in a real system you have to consider cell load and radio link situation, which would in reality reduce the data rates that can be seen by a certain UE. The lower table shows the uplink UE categories. Again, there's 5 of it, and again they differ in terms of the maximum number of uplink shared channel transport bits that can be received within a 1 millisecond transmission time interval. And the highest category here supports 75,000 bits, corresponding to 75 megabit per second peak uplink data rate. The reason for this is that 64 QAM modulation scheme is optional for the terminals in the uplink, so only the category 5 supports 64 QAM and can therefore support this high data rate value.
Christina, one question to the UE categories. Do we know on which categories the wireless industry is working on? So means which type of UEs we will see when LTE is commercially rolled out?
Yeah, of course. So for the downlink side, of course, 4 receive antennas at the terminal is very ambitious. So we won't see that in the near future. But having 2 antennas at the terminal and supporting the true MIMO spatial multiplexing, that's definitely coming. So we will probably see UE category 4 in downlink definitely coming. Also for the uplink, the highest category is probably quite ambitious, supporting the 64 QAM. So we will see the other categories initially.